Hey everyone, welcome to Data Platform Summit 2021. My name is Velida. I'm an Azure Integration Consultant working for Datacom Systems in Auckland, New Zealand, and I'm also a Microsoft Data Platform MVP. And in this session, we're going to be talking about data modeling in Azure Cosmos DB, Microsoft's globally distributed multi-model database service. Whether you're coming from a relational data background and you're completely new to Azure Cosmos DB, or if you're very experienced with Cosmos DB and you've been using it in anger for a while now, the purpose of this session is to help you, no matter what your experience level, understand how you can model your data correctly when building applications that use Azure Cosmos DB. Now, before we start, just a huge shout out to Microsoft for supporting the Data Platform Summit this year. During the conference, make sure you pop into their virtual stand and send them your thanks for supporting this great conference. So in this session, what I'll be doing is I'll go over, start at the very beginning and go over what Azure Cosmos DB is. Then we'll move on to why developers are opting for NoSQL databases and what benefits they provide compared to SQL databases. Then I'll talk about how data modeling is slightly different in Azure Cosmos DB to what data modeling would be in relational data stores. And then we'll dive into what techniques we can actually implement when we're modeling our data for Cosmos DB applications. And then after that, we'll touch into a little bit how partitioning works in Cosmos DB and how that factors into the designs of our data models. And then we'll finish off with a demo. So to start off, to really explain what Azure Cosmos DB is, Azure Cosmos DB is Microsoft's globally distributed multi-model database service. Using Azure Cosmos DB, we can build databases using a variety of different data models. We can build applications that use document models using either the SQL API or MongoDB API. We can build applications that use columnar data using the Cassandra API. If you've worked a lot with Azure Table Storage and you need like a globally distributed version of Azure Table Storage, Cosmos DB provides a table API that allows us to work with key value data. Or perhaps you're building applications that use graph data, and if you're building those sort of applications, you can use the Gremlin API, and that helps you store your graph data inside Cosmos DB. No matter what API you're using, Cosmos DB provides us with the ability to build highly responsive and available applications worldwide, ensuring that no matter where our users are in the world, we can bring their data as close to them as possible. And the key benefits of Azure Cosmos DB is really that turnkey global distribution. So essentially Cosmos DB will replicate your data to wherever your users are. And we can add and remove Azure regions to our Cosmos DB accounts at any time. And what Cosmos DB will do is replicate our data to all of those regions associated with our Cosmos DB account, while allowing our applications to continue to be highly available. You also get elastic scalability of both throughput and storage worldwide. So Cosmos DB offers us elastic scalability for reads and writes all across the globe. We can scale from thousands to millions of requests per second, and we only pay for the throughput that we need to help deal with any spikes in our workload. There's guaranteed latency at the 99th percentile worldwide. So with Azure Cosmos DB, like I said, we can build highly responsive planet-scale applications. And what Cosmos DB guarantees is less than 10 millisecond latencies for both index reads and writes at the 99th percentile, which helps provide rapid queries and responsive applications. Cosmos DB also comes with precisely defined multiple consistency choices. So with Azure Cosmos DB, we're no longer forced to choose between two consistency extremes, eventual and strong. Cosmos DB provides us with 5 well-defined levels of consistency for us to choose from, depending on what our application requires. And out of the box, there are no schema or index management required of Azure Cosmos DB, with some caveats. So out of the box, Azure Cosmos DB will automatically index all of your data and is schema agnostic, meaning that we don't have to worry about application downtime or managing schemas or indexes, anything like that. But there are caveats behind that, and some I will explain as we go through this session. So why NoSQL in particular? Well, NoSQL databases provide us with a couple of benefits. First off, they allow us to have flexible data models. NoSQL databases typically have very flexible schemas. With this flexibility, with our schema being so flexible, it allows us to easily make changes to our database as our requirements change. We can quickly iterate and continuously integrate new features and provide value to our users a lot quicker than we could with relational data stores. There's also horizontal scaling, so most SQL databases require you to scale up this massive server vertically when you exceed the capacity requirements for your current server. NoSQL, however, allows us to scale out horizontally, meaning that you can add cheaper commodity servers whenever we need to. There's also faster queries. Now, queries in NoSQL can be a lot faster than SQL databases. Why? Because data in SQL databases is typically normalized, so queries for a single object or entity may require us to join data from multiple tables. And as our tables grow in size, these joins can become expensive. However, data in NoSQL databases is typically stored in a way that's optimized for queries, and we'll see that as we unfold this session a little bit more. It's a lot easier for developers. So some NoSQL databases, their data structures are kind of similar to that of popular programming, or to this. They're very similar to the data structures that we'd find in popular programming languages, and this allows us to map our data, to store our data in the same way as we'd use it within our application code. Now, this may seem very trivial, but this mapping can actually allow us as developers to write less code, leading to faster development time and fewer bugs in our code. So how can this apply to Azure Cosmos DB, and what kind of initial questions might we ask when we're starting to model out our data for our applications? And when developers and data professionals ask me questions around data modeling for Azure Cosmos DB, this is kind of like the general gist of, this is the common set of questions that I get asked as someone who's worked with Cosmos DB for a while. So the first question I get asked is, why should I care about data modeling in Cosmos DB when it's a schema-free data store? How is data modeling different in Azure Cosmos DB compared to what data modeling is when we're developing applications that use relational data stores? And how can we express relationships in our data store, bearing in mind that Cosmos DB is a non-relational data store? So how can we actually express those relationships as data within our applications will naturally have those relationships? So for this purpose and to answer these questions, we're going to use an example of an online bookstore. So imagine that we have this application where we store information about books, authors of those books, and in this example we could hold information about the reviews of those books, or what kind of comments that customers would make on those particular books. And we might come up with a very simple relational model like so. So with relational data stores, we would normalize our data and break each entity into discrete components. So here we might have a discrete entity for an author. We'll have discrete entities for books and reviews. Books, when we're starting to think about relationships, a book will have an author. Books might have multiple reviews that customers have made on those books. Authors can have write multiple books. The basic idea here is that with normalization, we're trying to avoid storing redundant data and then refer to other data when we need to. So for example, if we wanted to retrieve all the books that were written by a particular author, we might write a query something similar like this. So essentially to get a book for an associated author, along with all the ratings of the books that they've written, we'd need to use joins to denormalize their data to us whenever we want to see that information. Now, alternatively, updating all of this information would require us to perform write operations across multiple and different individual tables. Now, This pattern of querying and writing our data isn't exactly new. We've been doing it for a long time. So you might be thinking, watching this, well, why wouldn't we take the same approach in Azure Cosmos DB? It does make sense to keep different and discrete entities in separate tables. And as you've said, Cosmos DB doesn't really care about document schema. So why would this practice not apply to Azure Cosmos DB? Well, there are several problems with this approach. Right off the bat, Cosmos DB doesn't have support across containers. Now, for those of you who are new to Azure Cosmos DB, you can think of a container as a table in SQL Server. And Cosmos DB doesn't support joins across containers. So right from the start, you won't be able to join data sitting in one container to data sitting in another in a query. That's not possible. Taking this approach also has cost repercussions, not just technical ones. We haven't talked about throughput, but depending on how you provision throughput on your databases or collections in Cosmos DB, having a bunch of different collections and managing those all over the place might not be the most efficient approach to take. And then finally, performing operations across these different collections will be messy. What you will have to do to compromise for no support for joins across containers, you might have to do this. You would have to do this in memory. So you'd be making multiple reads to your Cosmos DB collections, and then trying to update your data all over the place while your application's running. Which is it gets pretty messy. If anything should fail, or if anything should happen, you'll lose the progress of your operations. So with all this in mind, you might be scratching your head thinking, well, how can we actually model our data in Azure Cosmos DB? So with Cosmos DB, we have a few options at our disposal. We can use embedding in our documents. We can reference data in some documents that reference the data that's sitting in other documents. We can use a bit of both using a hybrid approach. Or we can be really ambitious by storing different document types, that is, different entities, within the same container, being the same table. But let's start off simple by taking a look at embedding first. So with embedding, we treat entities in our model as self-contained items within our documents. So taking this example here, I have an author entity with a book entity embedded inside our author document. Now, all the information related to this author is embedded in a single document. So querying for this author doesn't require any elaborate joins to multiple tables. Essentially, what we've got here is one document sitting in one collection, meaning one request. Getting this book or getting this author, retrieving it, is a single read operation, while updating it is a single write operation, which is really nice and simple and really straightforward. When can we use embedding? So the general guidelines for embedding are pretty straightforward. If we have contained relationships between entities, if we have one to few relationship between entities, if the data that we embed within our documents changes infrequently, if it doesn't grow without bound, say for example we have an array of books for a particular author and we know that's limited to a certain amount of books and it doesn't grow beyond an unreasonable doubt, making our documents larger and larger and larger, we can use embedding. And embedded, if our data is queried frequently together, that's a good use case for using embedding for our data modeling. Now let's take a look at referencing. Now, bear in mind that despite being a non-relational database service, we will still have relationships in our data for the data that we store inside Cosmos DB. Now, if we're finding as we're developing our applications and our relationships are becoming more and more complex, it would be better to stick to the relational data stores. So if you're finding that there's high complex relationships with between your certain pieces of data, and Cosmos DB isn't performing so well to serve those relationships, my advice would be to stick with those relational data stores. But if your relationships within your data is very, very simple, that's when we can use referencing. So let's take the following example. Now, some authors in our applications, they might publish more books than others, and it would be impractical to store all the books that they've written inside that same document. So what we could do to address this is add a reference to the books that they have written in another document. And this approach is great that if we have arrays in our data that are unbounded, or in other words, that can grow to an unlimited size. We can even avoid having the book array within our author document here by adding a reference to the author within our book document. So with referencing, we do have a couple of options at our disposal in order to optimize our data models. Now, here are the just basic guidelines that we should follow if we want to use referencing in our data, or if we find that our data kind of follows these patterns. That might be a good indicator that you should use referencing for your data modeling purposes. If you have one-to-many relationships or many-to-many relationships, we can actually benefit from referencing, particularly when it comes to performing heavy-duty write operations. So if your document, if part of your document is being updated frequently, it might actually be better to extract that data model, stick it in its own, within its own document, so the write only affects that document rather than the entire payload. If our reference data then grows without bound, meaning that the reference data has an unlimited size, then referencing this data is a very good approach to take. And of course, thanks to the schema-agnostic nature of Azure Cosmos DB, we aren't limited to choosing one approach. So we can use a hybrid of both embedding and referencing, depending on the nature of our data. And here's an example. So here I've got my author document with a book that's embedded within this document, but then I've got another property, Ward, a award property that's referencing, and it's got the ID for that award, which might be referenced to data that's referencing data in another document. The general guideline here is that if embedded data that's used frequently with this document, we can actually embed it so we can retrieve that data easily. And the reference data that is still important but is less frequently retrieved, we can actually reference that data since we don't need the entire payload coming back to us as in our query results. The general idea is think about how each entity within your document is going to be used and accessed by your applications. Now, I suspect you might be thinking that with this approach I'm being a little bit too ambitious here. But with Cosmos DB, we can actually use multiple document types and store multiple document types within the same container. Now, relational data stores emphasize one entity per table, but in Azure Cosmos DB, we can actually store different entity types within the same container or the same table, thanks to the way that we can partition our data. It does feel a little bit weird, but it can actually improve the performance of our application and save us money. If we're accessing our data in similar ways, we can use different document types within the same container to help querying with our data. And let's use an example. So in this example, what I've got two documents, one that summarizes my activity data for a day, and another document for that summarizes my sleep over a particular day. Now, what I've done here is I've partitioned by this property type, document type. Now, being able to partition my data that way, I can actually query both documents without needing a join by running a query just to retrieve those documents on a particular date. So rather than just selecting the activity table and then joining my sleep table, table to that query to get these this information back, I can essentially just run this very simple select query where the date is equal to the 7th of July 2021, and I will get both documents back. And this moves on really nicely to how we can actually partition our data in Cosmos DB and how partitioning influences the design choices we make when we're actually modeling our data. So how does partitioning work in Azure Cosmos DB? Partitioning is used to scale individual containers in a database to meet the needs of our applications. Every time we persist an item into our container, they'll be divided into something called logical partitions. And these are based on the value of a partition key that we've associated with an item that we store in our containers. Items within a logical partition will all have the same partition key value, and this will be a property within our documents. So say for example, I had a container that was storing items related to hotels, and we gave that container where we're storing our hotel entities a partition key value or a property of city name, and we had 20 different city name values in our container. For that example, we would have 20 logical partitions created for that container. These logical partitions are then mapped to physical partitions, and these are an internal implementation of the partitioning system, and this is just managed by the Azure Cosmos DB. This is essentially just a fixed amount of reserved SSD-backed storage and compute. So it's actually better if we illustrate this with an example. So in this example, let's say that we have a container containing hotels that's partitioned by city name. So every time we add a document to our hotel container that has a city name value of Auckland, it would be placed inside that logical partition. And let's say we add a bunch of documents, and each time new logical partitions are created as we're adding documents with hotels that situated all across the world in different locations. New logical partitions will be created to accommodate for these new locations. These logical partitions will then be mapped to physical partitions. Now, one or more logical partitions can be mapped to a single physical partition. So here we have our logical partitions for Auckland, London, Redmond, and Paris, all placed inside our physical partition here. Now, depending on the size of these logical partitions, we may only ever require a single physical partition. Remember that we don't manage these physical partitions ourselves. The Cosmos DB team does that. But there are a couple of things that we do need to consider, there are a couple of things that physical partitions really depend on. First off, the amount of throughput that we provision on our containers. Each physical partition can provide a maximum of 10,000 request units. Now, I've been in situations where I've been working in a team and we're developing our application, and we've noticed a little bit of slow performance. So what we've done is we've cranked up the request unit amount to 1 million. And this doesn't work due to the limitations on the physical partitions. So again, rather than thinking, oh, we have to scale vertically by just provisioning more request units, what's actually happening is as we're provisioning more request units on our Cosmos DB containers, that's actually scaling out. So more physical partitions behind the scenes are being created, and our data will get mapped to different physical partitions, and this does cause performance issues, as I'll mention a little bit later. And also the amount of storage that we're storing. So each physical partition can store up to 50 gigabytes of data. So as soon as we're adding items once we've added enough items to exceed that storage limit, a new physical partition will be created on the back end. Now, there's no limit to the amount of physical partitions that our containers can have. As our data grows and the amount of throughput we provision grows, Cosmos DB will automatically create new partitions by splitting existing ones, and this will happen without affecting our application's availability. When our physical partitions split, the data sitting in a logical partition will still remain within the same physical partition. All that happens with the splitting of physical partition is a new mapping of the logical partitions, our existing logical partitions to the new physical ones. So with this in mind, we need to start thinking about what kind of partition key we'll need to implement depending on the workload that our containers will be performing. Now, for read-heavy containers, we may choose to pick a partition key property that appears frequently as a filter in the queries that we perform. As we're developing our application and we're finding that we're querying frequently on a certain property, we might come to the conclusion that this would be a really, really good choice, or this property would be a good choice for our partition key. For write-heavy containers, what we may want to do is use the ID of a document as the partition key value instead. So the ID is guaranteed to exist in every item that we persist into our Cosmos DB containers, and this item ID has to be unique. So this can really help us achieve even distribution in terms of throughput and storage. And if we have to query our items that for this write heavy container, we know this item ID when querying it, which is really, really great for performing efficient point reads. Now, why the focus on partitioning and Cosmos DB as a whole and its relation to data modeling? Well, we can actually help Cosmos DB optimize our query by specifying a partition key as a filter. So in this example, what I've got is I've got a hotel container that's partitioned on a city name. And every time we query it, what Cosmos DB will do underneath the hood is route the query to the physical partition where this partition key value is mapped to. And what's great about this is if we add additional filters to this query that we're performing on the slide here, if we add additional filters to it, it would still filter to that single partition. Adding additional filters to our query doesn't change it, so we can really optimize our queries by specifying our partition key value within them, so we can ensure that queries are effectively routed to that logical partition in our Cosmos DB container. Now, however, say if we partitioned our hotel container by, say, a star rating property, and we wanted to query our container to return all the hotels with a star rating that's greater than 4. Think of a 5-star rating system for hotels, and I want to return all the hotels that have a star rating greater than 4. Then this query, it wouldn't be scoped to a single partition. This will actually cause our query to be executed across multiple partitions, or what's otherwise referred to in Cosmos DB as a cross-partition query. Now, cross-partition queries are essentially queries that don't filter on partition keys. So if we perform our query without specifying our partition key as a filter, what the query will do is fan out to all physical partitions where it'll be run against each partition's index. So each physical partition has its own index. So when we run a cross-partition query on a container, what we're essentially doing is we're running that query per physical partition. And what Cosmos DB will do is actually aggregate the results across all those different partitions, and it will cause a little bit of a bottleneck, because in order for our query result to be returned back to us, we'll have to wait for all of those physical partitions to execute that query and return the results of the query before the overall query is effectively done. And just to visualize this a little bit further, so here we're performing our query to retrieve all the hotels in a container with a star rating, well, less than 4 now. Our container is still being partitioned by city name, so here we're performing a cross-partition query. When we execute this query, it won't be routed to a specific partition. So what we have to do here is wait for the query to be finished on all of these physical partitions. In this example, I've got 3, but imagine if you've got 5, 10, X number amount of physical partitions. So you can see how this query can be very compute expensive and take a lot of time to process. We'll have to wait for that query to be finished on all physical partitions before the result of that query is returned back to us. And because of the way that logical partitions are mapped to physical partitions, it might be possible that we're querying a physical partition, using this query, and there's no items on there that satisfy our query. So we're essentially wasting compute cycles, processing a query, and waiting for that query to be returned back to us when there could be no results for that particular query at all. So you can see how that's very wasteful. All right, that's the end of the theory. Now what we're going to do is we're going to just kick off into a quick demo. Okay, so in this demo, what I've got is I've got a database for my books application called Books DB. And as you can see here, I've got some containers within that database. So I've got an author container, an author v2, and I'll explain why that's v2 in a bit. A container for books called books, a hybrid container where I'm storing multiple, different types of entities within the same container, and then also a reviews container. So say if I want to retrieve a review for a particular book belonging to a particular author. So essentially in these containers, if I open up the items, I've only got one item in here, and this is the author entity that I'm dealing with. If I go into books, I have several more books, and this is what my book entity looks like. So it's got attributes or properties for book name, genre, release date, average rating, and also an author ID to indicate which author it belongs to. And then I've also, in my reviews container, I've got a review entity as well. So the ID of the document, the book ID saying that this review belongs to this book, what particular rating this reviewer has given to the book, and a description as well saying whether it's okay, or maybe it's a bit more descriptive of that. I've also got a discriminator type property here called reviews, and I'll show you what that's for a little bit later. But let's say I want to get a particular review for a book. So if I just close all of these, I'm going to go into my author container. I'm going to create a new query, and I'm going to go select star from C, where C.id is equal to, and I've got a ID off screen, which I'm just going to copy and paste into here, and just execute that query. And simple enough, we have our author entity returned to us. But the thing of note here, and I want you to just keep this in the back of your mind as we're going through this. If I go into my query stats, I've spent 2.83 request units on getting that. Actually, zoom in's not going to work out so hot for me. I've spent 2.83 request units on getting that result back to me. So let's actually open up a calculator here. And I'm going to keep track of this. And hopefully you guys can see where I'm going with this. Okay, so we've got our author entity. So now I want to get a book, I want to retrieve a book where the particular author, with that particular author ID. So select from C, where C.author ID is equal to, I'm going to just copy and paste my author ID from earlier. Execute that. Sweet. So here I've got a list of books belonging to that particular author. And if I look at the query stats now, that cost me 3.13 request units to retrieve back. So if I just go 3.13, so we spent just under 6 request units so far. And now what I want to do is I want to query my reviews container where C.bookID is equal to a book ID that I've stored earlier. Just execute that query. And here I've got a bunch of reviews for that particular book. Let me just get some more real estate on here. And if I look at my query stats, I spent 3.32 request units on that query. So if I go 3.32. So overall, executing these 3 queries, 3 separate queries, I've spent 9.28 request units. And bearing in mind what I've done here is I've called my Cosmos database 3 times in order to get these results back to me. So you have got, essentially what we're doing here is we're actually making life a little bit more difficult for us. We're actually making more calls to the database than we need to. If something was to go wrong in between one of the calls for whatever reason, we'd lose our results and our query wouldn't be returned back to the user, or would be partially corrupted. So essentially what we'd like to do is create a data model where we'd only have to call the database once and it will retrieve all the information that we need for that particular query. So let's take a look at that. So let's start off by running a query that allows us to not only, when we query the author container, so this author v2 container here, when we query that container, we're not just getting the author back, but we're also getting the books that that particular author has written. So if I create a new SQL query here, what I'm going to do is just go from C where c.author.id is equal to my author ID. Just copy and paste that. Execute that query. And here I've got my author, so there's me with my author ID and all the books that I have written. And that query itself, 2.88 request units. So as you can see, what we've done here, we've actually embedded our book entities within the author document. And that way we've just made a simple request to our author v2 container where it's just essentially said, okay, for this particular author, retrieve that document. And not only have we just got the author entity returned back to us, but we also have all of these book entities returned to us as well. So just to re-emphasize, here we're treating our book entities as self-contained items within this document. So I have my author entity here, and embedded in this document, I've got my book entities embedded inside this author document. So all of our information related to this author is now embedded within a single document. So querying this is just a simple read query. So there's no elaborate joins here. There's no multiple tables. This is just literally one container, one query. And updating this is actually really simple as well because it's a simple write operation. So if you have data that has contained relationships between your different entities, there's one to few relationships between those entities. If this data doesn't change infrequently, so I might only write, or this particular author might write only a certain amount of books within their lifetime, and it doesn't, the information about these books aren't going to change frequently. It's not going to grow without bound, and it's likely that we are going to query this data together. So this is a really good candidate for actually embedding our data within the same document. Now you might be looking at this and thinking, well, this works at a very simple level. There's an author, there's only so many books that particular author has written, but what about reviews? There's still that relationship between reviews the books and the amount of reviews that a particular book has received. So if we were to deploy this model in production, we'd still find ourselves having to query our Cosmos database at least twice, not only to retrieve our books within this particular author document, but then also getting this book ID and then trying to match it up with the ID of a review that's sitting in a separate container. So what we can do as well, if I look at this document here, what I've done is I've added this reviews ID to, just give myself a little bit more real estate here, just zoom in. So I've added this review IDs array within my embedded books entity. So within this books entity, I've got the name, I've got the genre, release date, author ID, etc., average rating as well. But I've also got a bunch of review IDs. So when I query this container, this information can be returned back to me, and I'd still have to use it to make another query to this container to retrieve the review properties, like the average, the rating of that particular review, and what was said about this particular review. But this approach is great because this data might be extremely unbounded. It might be a really, really popular book. Lots of people might want to share their opinion about it. It might be a really unpopular book, so they might just want to pan it and say, this is terrible, don't buy it, stay away. And it could grow to an unlimited size. So remember, if you have many-to-many relationships and there's data that's changing frequently, or particular parts of your data that's changing quite frequently, and it's going to grow without bound, this is a really good this particular property or bit of data would be a really, really good candidate to use referencing referencing techniques within your data. And
thanks to the schema agnostic nature of Cosmos DB, we can actually be really, really flexible about this. And you can see within this document, this is a real hybrid approach that we're taking here. So we've got an embedded entities within our documents. So we're adding a bit more description about our books within this author document. But then we're also using referencing to say, hey, there's data sitting in another container. It's changing all the time. There are frequent updates to it, but there is that relationship to that data, and we're just not spending the request units or wasting any request units, rather trying to update the same document that we have here. We'll leverage that responsibility to another container and let that container take the responsibility for heavy write workloads. So think about your data patterns and think about how you might want to leverage a hybrid data modeling strategy in those situations. And then finally, don't forget that thanks to the way that Cosmos DB partitions its data, we can actually store different document types or different entities within the same container. And this does feel a little bit strange when you're first using it, but it can improve performance quite a bit. And it's great for similar access patterns. So here I've got this container, which has got my author entity, book entities, and review entities all in the same container. And if I use another example, so if I go into, I've got a personal health application that I've been using to record my health data. And essentially all I've got is one container that does actually use a discriminator property to partition against. So I've got records for sleeping, nutrition, and exercise that I'm storing in here. And if I wanted to, I'm just going to execute a query. Say if I wanted to execute a query where I want to get all the documents for a particular date. So I'll just go C, where C, select star from C, where C date is equal to, let's do 08/21. If I execute that query now, here I've got 3 different types of documents returned back to me. So I've got my sleep document. I've also got my activity document, so how many steps I've done in a day, how many minutes I was active, stuff like that. And also nutrition. I forgot to log my food yesterday. But if I look at that query stats, I've spent just under 3 request units making a simple query. Now this is a cross-partition query, but what I've been able to achieve by adopting this pattern is essentially retrieve all different types of records within a particular date. And so I can actually query these documents without needing any joins. Remember, we can't join across different containers. And it's just a very simple query running against a particular date to retrieve these 3 documents back to me as a user. So really with this demo, just to kind of sum up the demo that I've done, is that it's really worth spending time actually thinking about how you're going to model your data and how you're going to model it in the context of how you're going to access it. So if you do need to query your Cosmos DB containers and get different types of entities returned back to you as part of that query, really spend some time thinking about how those different entities are, what their relationships are like, how they relate together, and think about how that's going to affect the way you store them in order to make your queries more optimal and really help you optimize your applications. We've got all different types of strategies, so we can actually embed entities within our documents. We can actually reference different entities. Say if we've got heavy writes going on in a separate container, but there is still that relationship, we can just have like a reference ID to that particular document. So we'll just let that container handle all the frequent updates, and that data can just sit there as kind of like the only static part of that data in another container. Or if we just want to keep things really cheap and we want to just really optimize how we store our data, we can use discriminator properties like we've done here for the document type, as I've done here in this container, and then we can modify. We can think about what properties we can store, which is common across all of our entities, to make our life a lot easier when we're actually querying our containers.
So just a few takeaways before we close up the session. Now, The big takeaway here is that just because Azure Cosmos DB is a NoSQL service, it doesn't mean that we can just throw data modeling out of the window. It's extremely important to get into the practice of data modeling when designing and developing your applications that are going to be using Cosmos DB as a data store. Traditional relational data modeling may seem like a natural fallback, but this approach will cause issues. A better way to approach data modeling in Azure Cosmos DB is to really think how you're going to be accessing your data. Ask yourself questions like, what kind of writes are we going to be performing? What kind of queries are we going to be needing to do? How can we model our relationships between our entities in a way that's flexible and in a way that ensures that our queries can perform quickly and can allow our applications to scale? Use the platform to your advantage. It may seem unnatural and ambitious to store multiple entities within a single container, but if it makes your life easier, if it makes your queries more performant, just go ahead and do it. Make sure that you understand how partitioning works and ensure that your partitioning strategy will help you to evenly distribute your storage and throughput. Make sure that when you're designing your data that they serve the requirements of your applications, and you'll be on a good path to creating high-performing applications with Azure Cosmos DB. Well, that's the end of the session. Thank you so much for attending. Just before I wrap up, there are just a couple of things I'd like to share with you. So the summit is giving attendees a chance to win prizes. There are 3 ways you can do this. Promote your attendance on social media, post a selfie, use the hashtag DPS 2021, and you'll be in to win some prizes. Give us session and conference feedback. What do you like? What don't you like so much? That feedback is really, really valuable in helping us as speakers grow and helping the conference get better and better for future years to come. And make sure that you visit the conference sponsors and exhibitors. Go check them out. Thank them for sponsoring this conference and see what they've got to offer you. Thanks for attending this session. I will be hanging out in the chat afterwards, or during the session, sorry, so feel free to ask questions. And if you do have any follow-up questions, feel free to reach out to me on social media. I've got my Twitter, LinkedIn, DevTio, and Polywork profiles there. Just bear in mind that I am in New Zealand, so there is a little bit of a time difference. So if I am a little bit delayed in getting back to you, I apologize ahead of time. But again, if you do have any questions, feel free to ping me there. Thank you everyone for attending. Stay safe, and I hope you have a fantastic rest of the conference.